SPC and data analysis in semiconductor fabs. Statistical process control, or SPC, plays a crucial role in maintaining high-quality output in semiconductor fabs. It allows teams to monitor, control, and optimize manufacturing processes through data-driven decisions. In this overview, we'll explore how SPC is applied alongside Six Sigma methodologies to ensure consistent and reliable production outcomes. Six Sigma provides a structured approach to identifying root causes of process variability, enabling continuous improvement and defect reduction. Quality control is a key focus, as maintaining tight tolerances is essential in semiconductor fabrication. Data analysis helps teams detect subtle trends, shifts, and outliers before they lead to defects. When implemented correctly, these tools drive manufacturing excellence by improving yields, minimizing downtime, and enhancing equipment reliability. This presentation is designed as an introduction for a general audience, operators, technicians, engineers, and managers alike, seeking to understand the role of SPC and data analytics in advanced manufacturing environments. Overview. This presentation introduces the foundational concepts and practical applications of SPC and data analysis in semiconductor fabs. First, we begin with SPC fundamentals, where we cover the basic principles behind statistical process control, including control charts and monitoring techniques. Next, we explore the semiconductor context, focusing on the unique manufacturing challenges within fab environments, such as high complexity, variability, and the demand for ultra-low defect rates. Then, we move into the Six Sigma methodology, emphasizing the DMAG framework: define, measure, analyze, improve, and control, as a proven path toward quality excellence. We will also examine key data analysis tools, including various statistical techniques and how they support decision-making. Implementation strategies will follow, offering best practices for applying SPC in real-world fab operations. Finally, we'll discuss benefits and ROI, highlighting how quality improvements and cost savings are realized. Key focus areas include process variation control, defect reduction, yield optimization, and overall cost efficiency. SPC fundamentals. Statistical process control, or SPC, is a data-driven methodology that leverages statistical techniques to monitor, control, and improve manufacturing processes. Its main goal is to reduce variation and maintain consistent product quality. In semiconductor manufacturing, this approach is especially critical due to the extreme precision required. First, it is essential to understand variation. Every process has natural variability, and recognizing these fluctuations helps determine what's normal and what's not. Next, we must identify causes of variation. By distinguishing between common causes, those inherent to the process, and special causes, which arise from specific events or shifts, teams can take targeted action. Lastly, SPC focuses on continuous control. This involves maintaining operations within statistical control limits, allowing for early detection of issues before they impact product quality. Together, these principles form the foundation for proactive quality management and continuous process improvement in high-tech manufacturing environments. SPC fundamentals. Understanding the two main types of process variation, common cause and special cause, is foundational to statistical process control. Common cause variation is natural and inherent to the process. It represents the baseline noise in any stable system. Although these variations are random, they are also predictable over time, allowing us to analyze performance within expected bounds. However, if performance improvement is the goal, then action must focus on redesigning or refining the process itself. On the other hand, special cause variation arises from external or abnormal factors. These are not part of the usual process and are therefore unpredictable and often disruptive. Special causes indicate the process is out of control and require immediate investigation to identify the root cause. Acting quickly on special cause signals prevents defects, equipment damage, or product scrap. Distinguishing between these two variation types is essential for effective decision-making and process stability in semiconductor fabs. Semiconductor manufacturing context. Statistical process control is absolutely critical in semiconductor fabs due to the extreme precision required in every operation. These manufacturing processes operate at the nanometer scale, where even the smallest deviation can result in major defects. There is virtually zero tolerance for variation. One reason is the sheer number of process steps involved, often over 1,000 from start to finish, each of which must be tightly controlled. Additionally, the weeks-long cycle time for a single wafer lot means that mistakes caught late in the process are extremely costly and time-consuming to correct. The feature sizes being produced are measured in nanometers, making the process highly sensitive to any variation. Finally, each wafer lot carries a very high value, making defect prevention essential to protect product yield and financial investment. These factors combined make SPC a vital discipline for ensuring consistent quality and operational efficiency in high-volume semiconductor production. Semiconductor manufacturing context. Semiconductor manufacturing presents significant challenges due to the extreme precision required. One of the major challenges is process sensitivity. Even a small temperature fluctuation of plus or minus 0.1 degrees Celsius during critical steps can result in serious defects, damaging yield and reliability. Next is equipment drift. Over time, process tools deviate from their optimal set points. Without continuous monitoring and calibration, this drift can lead to costly rework or scrapped wafers. Contamination control is also vital. In this ultra-clean environment, particles larger than 10 nanometers can destroy circuit functionality, especially as feature sizes shrink. On the quality side, manufacturers aim for yield targets of 85% to 95%, meaning nearly all chips on a wafer must function correctly. Defect density must be below 0.1 defects per square centimeter for memory devices. Achieving Six Sigma performance, just 3.4 defects per million, is the benchmark for operational excellence. Failing to meet these standards results in the cost of poor quality, where a single defective wafer can exceed $50,000 in wasted materials and processing time. SPC tools and techniques. Statistical Process Control, or SPC, provides a framework of tools to monitor, control, and improve manufacturing processes. Key among these tools are control charts, which help visualize process variation over time. The X-bar and R charts track average values and range, particularly useful when dealing with subgrouped data. Individual and moving range, MR charts, are ideal for monitoring processes with single measurements per time point. To assess defect rates, P and NP charts focus on proportions of defective units, while C and U charts track the count of defects per unit. In addition to charts, process capability analysis evaluates how well a process performs relative to specifications. The CP index measures process spread compared to the allowed specification width. A CP of at least 1.33 is desirable, though 1.0 is the minimum acceptable. CPK index adds the element of centering, with a target of 1.67 and a minimum of 1.33. Finally, the PPK index represents long-term capability, capturing both common and special cause variations, making it crucial for sustained quality control. SPC tools and techniques. Statistical process control relies on advanced statistical methods to manage complex manufacturing environments. EWMA, or exponentially weighted moving average, tracks small shifts by applying greater weight to recent data. QSUM, or cumulative sum control, is ideal for detecting gradual trends or drifts. ANOVA, or analysis of variance, helps compare variability across different process groups. DOE, or design of experiments, allows structured testing to identify which factors most influence process outcomes. In semiconductor applications, SPC is essential. Temperature control in CVD and PVD must be maintained within plus or minus 0.1 degrees Celsius. For critical dimensions, SPC tracks line widths down to the nanometer scale. Film thickness uniformity is controlled to the angstrom level. And electrical testing uses SPC to ensure leakage current and threshold voltages remain within limits. Real-time monitoring involves rules like 8 points on one side of the mean, 6 points trending up or down, or 2 of 3 points in Zone A. Finally, control limits in fabs are set at plus or minus 3 standard deviations from the mean. This captures 99.7% of normal process variation, helping to identify outliers early and avoid costly defects. Six Sigma Overview. Six Sigma is a data-driven methodology focused on reducing defects and enhancing quality by striving for high performance across processes. It aims to reach near perfection, typically defined as no more than 3.4 defects per million opportunities. This method relies on statistical tools and disciplined problem-solving to improve outcomes systematically and predictably. At the heart of Six Sigma lies the DMAIC methodology, a structured 5-phase approach. First is define, where teams clarify the problem statement, project scope, customer needs, and create a process map. Then in the measure phase, data is collected to establish baseline metrics, assess process capability, and validate the measurement system. Next comes analyze, which focuses on identifying root causes using tools like statistical analysis, hypothesis testing, and process flow studies. During the improve phase, teams design solutions, conduct pilot tests, develop implementation plans, and evaluate risks. Finally, in control, mechanisms are put in place to sustain gains. This includes control plans, SPC integration, training, documentation, and continuous monitoring. Six Sigma Overview. Six Sigma provides several key benefits within semiconductor fabs. First, it drives yield improvement, typically increasing production yield by 5% to 15%. This is critical in high-volume manufacturing environments. Second, Six Sigma leads to cost reduction by eliminating defects and rework, saving millions of dollars in materials, labor, and cycle time. Third, it enables cycle time reduction, helping new products get to market faster by streamlining processes. Finally, Six Sigma fosters a cultural change, instilling a mindset of data-driven decision-making across the organization. Six Sigma also integrates seamlessly with SPC. For example, control charts are used in the measure phase, process capability analysis supports the analyze phase, and real-time monitoring is crucial in the control phase. Common applications include wafer defect reduction, equipment optimization, yield excursion investigations, and new process validation. Quality levels range from 3 SECs with 66,807 defects per million to the Six Sigma gold standard of just 3.4 DPMO. Six Sigma practitioners advance through belt levels, from yellow belt for basic tools to green belt project leaders, black belt experts, and master black belts who serve as trainers and coaches. Six Sigma Overview. Six Sigma is a data-driven methodology aimed at improving business processes by minimizing variability and reducing defects. It is built on a structured problem-solving approach using the DMAIC framework: define, measure, analyze, improve, and control. One of the main appeals of Six Sigma is its focus on measurable outcomes, making it highly effective across industries, especially in manufacturing and services. In terms of success metrics, Six Sigma projects often deliver substantial cost savings, frequently in the range of hundreds of thousands of dollars per project. Project durations typically span several months, reflecting the rigorous analysis and implementation involved. However, the true value lies in achieving sustained improvements over time. These long-lasting gains are the result of robust control measures that ensure processes continue to perform at high levels long after the project has concluded. Data analysis in semiconductor fabs. Data analysis in semiconductor fabs starts with structured data collection across 4 main sources. Equipment sensors track critical parameters like temperature, pressure, flow rates, and RF power to monitor tool performance. Metrology tools measure key features, such as critical dimensions using SEM, film thickness, overlay alignment, and defect locations, to ensure process control. Electrical testing provides insight into device functionality using parametric tests, wafer sort evaluations, probe test data, and final yield measurements. Finally, automated systems, including MES and SCADA platforms, capture recipe parameters and manage yield tracking in real time for integrated control. Once data is gathered, statistical analysis is applied using 3 tiers. Descriptive analytics summarizes the current state through metrics like mean, standard deviation, range, and skewness. Predictive analytics forecasts trends and detects risks using machine learning, regression, time series, and classification models. Advanced analytics further extracts value through PCA, clustering, neural networks, and ensemble techniques, enabling deep pattern recognition and multivariable optimization. Data analysis in semiconductor fabs. In semiconductor fabs, real-time monitoring plays a crucial role in maintaining process control. Live dashboards offer continuous visibility into equipment status, process parameters, and yield trends. Alarm systems provide automated alerts for out-of-spec conditions or equipment malfunctions, enabling prompt corrective actions. Data streaming supports high-frequency data collection, up to 1000 Hz, capturing subtle process changes. Fast response time, often within subseconds, ensures rapid detection and notification of deviations to prevent scrap and downtime. To make sense of this data, fabs use powerful visualization tools. Trend charts illustrate time series behavior of key metrics, while heat maps reveal spatial variability across wafers. Correlation matrices help identify relationships between parameters, and Pareto charts prioritize defects and isolate root causes. Supporting these efforts, fabs deal with vast data volumes daily and rely on integration platforms like MES ERP for execution, SECS, GEM for communication, data warehouses for historical analytics, and cloud analytics for scalable processing power. Data analysis in semiconductor fabs. To measure the effectiveness of data analytics in semiconductor fabs, key performance indicators, KPIs, are used to track progress and outcomes. One of the most critical KPIs is data availability. Reliable access to complete and accurate data sets is foundational for any form of analysis or decision-making. Without consistent data availability, process control, yield improvement, and defect reduction efforts are compromised. Another essential KPI is alert response. This measures how quickly and effectively teams respond to automated alerts or flagged anomalies. A fast response time reduces the risk of yield loss and equipment damage, ensuring more stable operations. Finally, prediction accuracy is a vital KPI that evaluates how well analytics tools and models forecast future events, such as tool failures, defect trends, or yield excursions. High prediction accuracy leads to more proactive maintenance, better resource planning, and ultimately, fewer disruptions in manufacturing. Benefits and impact. Implementing statistical process control and data analytics in semiconductor fabs delivers measurable business value across multiple dimensions. In terms of yield, organizations often see a 50–80% reduction in defects, along with a first-pass yield exceeding 95%. Rework is significantly reduced, often by 60%, freeing up resources and enhancing throughput. From a cost perspective, data-driven improvements lead to annual savings through reduced material waste, typically by 30–50%. Equipment efficiency, measured through OEE, is boosted to 85% or higher. Additionally, labor productivity gains reach 25%, enabling the workforce to do more with less effort. On the quality front, companies achieve a Process Capability Index, or CPK, greater than 1.67. This supports tighter specification limits, enhances customer satisfaction, often reaching 99.5% quality ratings, and ensures consistent output. Finally, the competitive advantage becomes clear through faster time to market, improved market positioning, a 50% increase in innovation speed, and customer retention rates above 95%, reinforcing loyalty and long-term success. Benefits and impact. Implementing SPC and data analytics leads to measurable improvements across operational, financial, and strategic dimensions. First, operational excellence is achieved through increased equipment uptime, enhanced process stability, and reduced cycle times. Equipment uptime improves due to better predictive insights, helping prevent unexpected breakdowns. Stability in processes ensures consistent quality and fewer fluctuations, while faster cycle times allow quicker throughput and greater capacity utilization. Financially, the benefits are substantial. Companies can save $1.8 million through scrap reduction, $1.2 million by eliminating rework, and realize $2.2 million in value from efficiency gains. The return on investment is reached within 18 months, with implementation costs paid back in just 4 months, making this a financially sound initiative. Strategically, companies experience faster time to market with a 50% reduction in development cycles, a 15% market share increase, innovation driven by data-informed decisions, and strong risk mitigation through predictive analytics. Together, these gains offer a competitive edge. Benefits and impact. The adoption of SPC and data analytics dramatically improves operational yield and business outcomes, with industry benchmarks showing a compelling contrast. Without SPC, typical yield ranges from 60 to 70%. However, with SPC and analytics in place, yield consistently improves to a range of 85 to 95%. This difference not only enhances profitability, but also establishes a competitive advantage through higher product quality and fewer defects. The return on investment timeline is clearly phased. During months 1 to 3, efforts focus on setup and training. From months 4 to 6, organizations begin to see early savings. By months 7 to 12, the full benefits of the implementation are realized. This structured rollout ensures manageable change and measurable progress. SPC Analytics also delivers continuous value. Organizations report $5 million in early savings, growing to $8 million, and eventually exceeding $12 million in annual savings, highlighting sustained impact and long-term profitability. Conclusion and next steps. To transform semiconductor manufacturing with data-driven excellence, several key takeaways guide the journey. First, SPC, or Statistical Process Control, is essential. Statistical control ensures consistency, real-time monitoring enables immediate corrective action, and understanding process capability is critical for maintaining yield. Second, Six Sigma methods, particularly the DMAIC methodology, are proven to reduce defects and achieve quality excellence by driving continuous improvement. Third, data drives value. Analytics generate actionable insights, predictive models anticipate problems before they occur, and automation accelerates better outcomes. Finally, the return on investment is well documented. SPC and analytics lead to a 5 to 15% yield improvement, generate $2 to $10 million in annual savings, and achieve a payback period of just 4 to 6 months. The implementation roadmap spans 5 phases: assess current gaps, plan with strategic goals, deploy systems and pilots, optimize performance through tuning, and sustain gains with a culture of innovation and analytics. This is the foundation for long-term success. Conclusion and next steps. To launch a successful SPC and analytics transformation, immediate actions must be taken. First, form an implementation team composed of cross-functional experts. This ensures that both technical and operational perspectives are represented from the start. Next, perform a baseline assessment by documenting current performance metrics. This will be critical for measuring improvement. Then, conduct a vendor evaluation to explore the most suitable SPC software solutions available on the market. Finally, begin training planning to identify current skill gaps and design learning programs that will equip the team for long-term success. To support this journey, leverage essential resources. Utilize training such as Six Sigma certification, SPC software modules, and statistical analysis workshops. Follow established industry standards including SEMI E10, the AIAG SPC manual, and ISO 9001, and collaborate with technology partners, SPC software vendors, analytics platforms, and consultants to ensure a robust, guided implementation. Press Start to begin the transformation. Conclusion and next steps. Measuring success is a critical part of any transformation journey in semiconductor manufacturing. 4 key metrics help track the impact of implementing data-driven excellence. These include target yield, which reflects output efficiency; process capability, which measures how well processes perform within specifications; quality level, which tracks defect rates and overall product consistency; and financial return, which captures cost savings and profitability improvements. To get started, several support options are available. Begin with a consultation and assessment to understand your current baseline. Follow with a demo or proof of concept to visualize how the solution performs in your environment. Training and support ensure your team is prepared, while implementation planning helps structure the path forward. The question remains, are you ready to transform your semiconductor manufacturing with data-driven excellence? If so, reaching out to an expert is the first step toward unlocking sustainable success.